In this video, we're going to define and do some examples with the union, intersection, and difference of sets. So if A and B are two sets, the union of those two sets is the set A union B, and it's denoted in this way: A U B, or cup B, is equal to the set X, such that X is an element of A or X is an element of B. This is inclusive or, meaning that X is in A or X is in B or X is in both A and B. So this is inclusive. And it's read out loud as A union B. If A and B are two sets, the intersection of A and B is the set A intersect B. We just have the upside down symbol of what we had above, so an upside down U. A intersect B is equal to elements X, such that X is an element of A and X is an element of B. In other words, these are the elements that are in both A and in B. So as a quick example, let's say that we've got A is the set 1, 4, 9, and 16, and B is the set 4, 8, and 16. I'd encourage you to just pause very briefly and find A union B and A intersect B. All right, so let's look at these two sets, A union B. So that's all elements that are in A or B or both. So 1 is in A, 4 is in both A and B, 8 is in B, 9 is in A, and 16 is in both A and B. So that is the intersection. It itself is a set, so we do need these braces to describe the set containing those elements. We happen to have written them in ascending order, but remember, the order of elements in a set does not matter. A intersect B, that is all elements that are in both A and in B. So 1 is in A but not in B, 4 is in both A and B, and 16 is in both A and B, and the other elements are not in the intersection. So that's A union B and A intersect B. Here's a new definition. If A and B are two sets, the difference of A and B is the set A minus B, which is equal to all elements such that X is in the set A and X is not in the set B. So in other words, these are the elements that are in A but not in B. So here is an example again to try. So with the same two sets we had above, I'd like you to find A minus B and B minus A, the difference of those two sets. So pause and try those just for a moment. Okay, so if we look at A minus B, those are the elements that are in A but not in B. And again, this is a set, so we need braces around those elements. 1 is in A and 1 is not in B. So yes, 1 is in the difference of A and B. 4 is in A, but it is also in B. So 4 is not in the difference, A minus B. 9 is in A and it is not in B. So 9 is in this set. 16 is in A, it's also in B. So that's all there is. What about B minus A? In this case, that would be, 4 is not in the difference because it's in both sets. 8, however, is in B and it is not in A, so 8. And 16 is in B, but it is also in A, so it's not in B minus A. So it's just the set containing only 8. Let's see. Let's look at a few more examples. Actually, before we go on, I should just point out that in general, as we see here, this is not symmetric. Recall that A union B in general is the same thing as B union A. It's just the elements that are in A or B that has no order to it, so that is a symmetric relationship. Similarly, A intersect B is the same thing as B intersect A, not just for these particular sets we're talking about, but just in general. However, in general, A minus B for two sets is not necessarily going to equal to B minus A. So that's just a quick note about symmetry of these different sets. All right, so now more examples. So we'll start out with A and B being the same two sets as above, and now let's introduce a new set, C, being the set containing 1 and 9. And I'd like you to find the following. Find A minus C minus A, C intersect B, as well as A minus C cross the Cartesian product with B minus A, and the power set of A minus B. So again, I'd encourage you to pause, grab a piece of paper, and try those out. Okay, A minus C. So those are all elements that are in A and not in C. Here we see that 4 and 16 are in A and they are not in C. So 4 and 16 is the set A minus C. C minus A, 1 is in C, but it's also in A. 9 is in C, but it's also in A. So this would just be the empty set or the null set. There are no elements that are in C that are not in A. C intersect B, that would be all elements that are in the intersection in both C and B. We see that this is again the empty set. There are no elements that are simultaneously in C and in B. And now let's look at A minus C cross B minus A, the Cartesian product of those sets. I would do it in steps. So I would first find A minus C. A minus C actually we've got above, that's 4 and 16. Cartesian product with B minus A. So the elements that are in B but not in A. 8 is the only such element that is in B but not in A. And now when we do the Cartesian product of those two sets, that is a set of ordered pairs where the first element of the ordered pair is in the first set and the second element of the ordered pair is in the second set. So this is our collection of ordered pairs that are in that Cartesian product. So this is our final answer. And finally, the power set of B minus A. So, the power set of A minus B, sorry about that. So that is the power set of the elements that are in A that are not in B. So looking back above, A minus B, 1 is in A but not B, 9 is in A but not B. So that's the power set of 1, 9, the set containing 1 and 9. Now the power set of this is the set of all subsets of that set, the collection of all subsets of the set 1, 9. So the empty set is a subset of every set. Here, the set containing just 1 will also be a subset. The set containing just 9 will be a subset. And the entire set itself is a subset as well. So that is the power set of A minus B. Here's one more collection of example problems to work on. So notice that in 1 through 4, we're looking at sets that are closed intervals on the real line and looking at their unions, intersections, and differences. So I'd like you to find those in 1 through 4. And then in part 5, we're actually going to sketch these sets on the xy plane. So let X be the set that's the Cartesian product of the interval from 1 to 3 closed, crossed with the closed interval from 0 to 2. And let Y be the closed interval from 0 to 2, crossed with the closed interval 1 to 2. So sketch the sets X, Y, X union Y, X intersect Y, X minus Y in the plane. So if you haven't already, do grab a piece of paper, sketch each of those sets, and we'll talk about them together. Okay, so first of all, the closed interval 1, 4 unioned with the closed interval from 2 to 8. So let's just draw this out in the real line. So if we're in the real number line, and we have the set from 1 to 4, and that's closed, so because it's a closed interval, we'll draw that with closed circles, as well as the closed interval from 2 to 8, all the way up to 8. So the union of those two, that will be any element that is in one set or the other set or both. So we see that everything from 1 to 8 inclusive is in one set or the other set or both sets. So that's the closed interval from 1 to 8 would be the union of those two. When we look at the intersection of those two sets, the intersection is only going to go from 2 to 4 inclusive. So that would be 2 to 4 inclusive, and that's still a closed interval because yes, 2 is in both sets, and 4 is in both sets, and everything in between is in both sets. So the intersection is going to be that closed interval from 2 to 4 inclusive. How about the difference? The set 1, 4 closed minus the set 2, 8 closed. So if we're looking at the difference of those two sets, here's the set from 1 to 4, and we're subtracting away everything that was in the set from 2 to 8. So everything that's originally in the blue set minus the things that are in the red set. Or the second set that I've drawn, if you happen to be blue-red colorblind, I apologize. I think it still works without the colors though. So what do we have in this first set? We do have 1, we have everything up to, but not including 2, right? So in the difference of these two sets, we have 1 that's in the first set, but not the second. We have, 1.1, 1.5, everything in here, all the way up to 2, but not including 2, because 2 is in the second set, and so it is not in the difference of those two sets. So this is a half open interval from 1 closed to 2 open. If we wanted to draw it, it would look like this on the real line, from 1 closed to 2 open. And last one, if we're looking at the set 2, 8 closed minus 1, 4 closed. Again, so here we've got 2 to 8 closed minus 1 to 4. So 1 to 4 closed. So everything that's in the set above minus everything that is in the set below. So we're just interested in the elements that are in the upper set but not in the lower set. So we see that 8 is in the upper set but not the lower set, down to 4. And so we have again a half open interval. This would be from 4 open to 8 closed. And this is the picture of that set. But in terms of interval notation, this is what we would write. Okay, finally, we want to sketch these sets in the plane. So X is the Cartesian product of 1, 3 crossed with 0, 2, both closed intervals. So we always assume that if we're drawing these in the plane, the first set is along the x-axis, the second set is along the y-axis. So from 1 to 3, and from 0 to 2. So this is just going to be a rectangle in the plane. And so this is our set X. Now our set Y goes from 0 to 2 in the x-axis and goes from 1 to 2 in the y-axis. So again, we've got a rectangle and it's there. So here is the set Y when we sketch it. The union of these two sets is everything that's in one set or the other set, or both. And so we've got everything that is in Y going from here to here, and everything that is in, everything that is in Y going from there to there, everything that is in X starting at 1 and going up to 2, and then going as well to 3. So here is X, and there is some intersection right there. So this is X union Y. X intersect Y is just going to be that little box that we sort of see drawn here, this intersection. And so that's just a unit square over 1, 2 here. So this is the intersection of X and Y. And lastly, the difference of X and Y, the elements that are in X but not in Y. So that would give us the things that are in X and not in Y. So there is X minus Y right there.